Hey everybody, and welcome to another edition of From the Desk of Lady Ada. You might be wondering, where am I? Well, I'm still in my room, and we have a new featured desk. We're going to be doing the EE bench now. This is where I actually get to do my work at home, and it's a lovely little EE desk. And I thought to inaugurate this new desk, I'd do a little teardown, maybe a historic teardown of this Heathkit et-3100 series electronic design experimenter. This is a really beautiful device, and I certainly didn't purchase this. I've never seen this before, but a lovely viewer has sent it. I'm just going to read briefly from Jim Grace. Jim writes, enclosed is a Heathkit electronic design experimenter model ET3100 series 06829 and 3 DVDs containing scans of the Heathkit manuals and the Heathkit Continuing Education Program courses. I guess it uses this. The design experimenter has not been plugged in for a long time. If you have a good engineer handy, hopefully, you might want to get them to look it over before power is applied. And then there's raster images inside, and there's audio files as well. So I guess there's some sort of educational series on here. But Jim says, I hope the material brings a smile. Any problems, questions, let me know. Thank you, Jim, for sending us this gift. We're going to take it apart and check it out. We did get this schematic, which was lovingly distributed with this, which will help a lot because I didn't really want to reverse the schematic. Not a lot going on inside of this thing. As you can tell, this is the entirety of the schematic, but still better to have somebody get the original than to try to reverse engineer it on your own, if possible. So let's go to the overhead cam and start looking at this thing. We're on the overhead? Okay, great. So this is the Heathkit Electronic Design Experimenter. Comes with a non-polarized 2-prong cord. It's got a power supply, so you can adjust the power supply positive and negative, and there's a ground. There's a 15-volt AC plus and minus here, 30 volts total. This is the line frequencies. There's probably a transformer inside of here. Looks like on the schematic there's a wound transformer. Back in the old days when it was totally cool to sell power supplies that use those. There's a frequency generator in here as well that ranges from 200 hertz to 2 kilohertz in one range, and then 2 kilohertz to 20 kilohertz. So good for audio level. Get sine and square. And then looks like over here there's 2 just potentiometers with nice knobs, and you can just use these potentiometers, and they give you taps for them, and then mini breadboard as well. I just want to, before I start taking this apart, I want to just respect this awesome font action here. Like, look at this Q. This I want to marry this Q. This is a beautiful silkscreen work. And it's an ABS case, and it looks like some sort of like metal or metallic faceplate. Really beautiful. They did a really nice job with this design. Not sure exactly when this was made. Maybe we'll find a date on the inside. So let's try powering it up and seeing what happens. So that's my power cord. I will plug it in underneath. We're back. Okay, nothing on fire yet. Let's try turning it on. Okay, when you turn it on, you get a little LED or bulb over here. And nothing smoking, nothing squeaking. So maybe let's try going to scope cam, and we'll probe some of these elements here. Let me grab this for ground line. So first up, let's check out this line frequency. So apparently this is 30 volts AC. Turn off that one and squidge this in. Oh my goodness, this is many volts. Okay, bring it in. Okay, there we go. So we'll measure this, and yep, 60 hertz. This is definitely line out, and it's 24 volts peak to peak. And so you might be wondering, well, wait a minute, why is it 24 volts peak to peak when, it's supposed to be 15 volts AC? Well, there's 2 reasons. One is you know, on the inside of here is a transformer. This is pre-regulated, so depending on the loading of the transformer, this voltage it's meant to be like at least 15 volts AC when loaded. And second, you know, they might be saying 15 volts AC, not peak to peak, but RMS, although it doesn't say that, so I'm not sure. It's probably does they mean it's at least 15 volts AC. And then there's also a negative 15 volts. Let me, 1 second. Oh, can you pass me that little orange wire?
Which one?
The little one right there. Yeah, the one underneath there. Okay, thank you. Just need another wire. So let's look at the other 15 volts AC. Turn that on the other one. So yeah, you can see they're exactly 180 out of phase. That makes sense because you've got 2 taps off of the transformer. And together, opposite, they're a total of 30 volts AC, which is really going to be more like 50 volts peak to peak. Next up, let's look at, there's a positive and negative power supply. So we'll tap into that. And let's look at the positive supply first. So yeah, you tweak the knob up and down, and you can get a range from 16.8 volts max down to about 1.5, 2 volts. Likewise, the negative, let's do period mean. The negative supply goes from about -1 volt all the way up to, or down to -15.5. So it's kind of handy. You get like a nice adjustable positive and negative supply. It's rare to be able to get a negative supply these days because usually you don't have transformer supplies. Supplies tend to be switching these days. Next up, let's check out this sine wave. It's got sine wave out, so let's look at that. Turn off this channel. Okay. All right, so we've got a 3.5 volt peak to peak, 20 kilohertz. That's because it's tweaked all the way. Let's shrink it down a little bit. It looks like, you know, as you move it, it's a little unstable, but once you get to the place you're going, it's stabilized down to about 1.75. It says 2, but you know, you definitely want an oscilloscope to verify what you're getting. Yeah, that's a nice sine wave actually, very nice. And then the square wave. The square wave is not AC coupled, or like it's not ground middle reference. The square wave is actually 0 to 18 volts, which is kind of ridiculous, but okay, maybe you just need a really high peak-to-peak square wave, and then yeah, you can adjust this frequency as well. So this works too. So far, everything on here works, which is awesome. Looks like the duty cycle's not exactly 50%. That's fine. You just want a square wave. You can maybe hook up a speaker to this later and get some squeaking going on. Okay, so we tested everything. We got the line frequency works, so that's good. So the power supply works, that's good. Power switch works, and the generator works. This actually is in excellent condition, which is great. So now it's time to open it up. Let's see what's inside this beast. Thank you, Scope Cam. You've done well. So first up, of course, unplug. And we can turn this over. So on the bottom here, you can see it's indeed et-3100 model. Look at this beautiful foil sticker. I mean, that's great. I'd love one of those. Disconnect line cord before opening. What's nice is they don't say warranty void if open. They just say, hey, just be safe, disconnect. 120 volts AC, 50, 60 hertz. Looks like it can work in Europe, even though it comes with an American cord. So we've disconnected it, and I've actually unscrewed a bunch of these because I just wanted to make sure that there was nothing inside that was before I plugged it in before. So I should be able to I have to undo the 2 screws in the top that hold this down. Okay. Got these. So yeah, I removed the this back screws just to get it so we would go faster. And you can just lift this up and split it like that. So inside here we've got, this is that line voltage in. This is, what is that? Caution. So looks, this is the fuse inside of here. Let's not mess with that. No need to mess with the fuse. And here's that transformer. So yeah, this is a big coil in tapped around here with a metal ring. And the 2 coils on either side basically allow you to step down the AC voltage from 120 volts AC or 240 volts AC down to about 30 volts AC. And also it gives you a split output. So you've got, you can tell you've got a plus and minus, as well as this is probably your center tapped. It is a floating supply, which is kind of nice. It's not a reference to earth ground, so you don't have to worry about like if your earth ground is actually tied to earth. I'm pretty sure they didn't reference it to earth. You can, no, looks like it is not, which is kind of nice. So even though this has a ground symbol, it's not earth ground. It's just a local ground. And then you can see over here, this is that switch, that power switch. So you've got a nice power switch that goes into here and switches off the power on the 120 volt AC side. And then you can start seeing that parts of the power supply here. You got these gigantic capacitors. And this circuit board, which is, you know, it's just, I don't know if this was made with a CAD program. It looks almost like it was hand-drawn, very kind of rounded shapes. And over here especially, it's definitely drawn by hand because, like, this is not like a perfect line. It's like you can see that there's variations. It's tinned afterwards, and the tinning is held up very well. And in some places you can see that they actually soldered to the tin. So this is the ground plane. You can just tell it's just this gigantic ground plane. So let's remove this PCB so we can look at the components on the other side. It's going to be a lot of screws. Let's undo. The interesting thing is, like, they have some free wiring going on over here. I'm not sure why they didn't put those components on the circuit board, why instead they decided to sort of solder them in place. Especially since it's like you can see there's this heat shrinking kind of going on here. It's kind of a lot of effort. I'm sure there's a good reason for it. Okay. So let's see if that's, oh, missed one. And missed another one. Okay, almost done here. Okay, so we can remove this top and just look at this. So, interesting design. The front panel is silk screened, and it's also where all the components are. So you've got all the components very nicely labeled here. You can see every diode, the transistors are labeled, the resistors are labeled. Underneath the resistors, there's actually the value of the resistors. It's kind of hard to see from the video, but just you can tell that it's printed inside the box. Each transistor not only is labeled with the part number, but also the emitter, base, and collector, which is kind of neat. So this is that power switch, and over here you can see a neon bulb. So, neon bulb can run off of 120 volts. It's a great way to have an indicator. They have that nice, lovely glow. And of course, you can run them off AC, so you don't have to worry about, making a little regulator if you wanted to do an LED instead. Okay. yeah, kind of interesting design. So it's, the back is just all the copper, and it looks like there's a couple of jumpers on the top, but for the most part, all the components are up here. So let's start taking a look at what's going on here. Well, first off, this switch is pretty straightforward. You've got a switch, and you've got the neon bulb. So that's going to be over here, this section. So there's a fuse, this is the power input, fuse, on-off switch, and then a neon bulb, and then there's a 27K resistor in series just because you want to not connect the neon bulb directly. And then we know that there's that transformer, and then the transformer comes out here, and then there's 3 wires, AA, BB, and CC. And you can see here there's 4 diodes, 1N 4002s. So these are signal rectification, power rectification diodes. And when you see 4 of these, or sometimes they're in a one package, you know you're looking at a full wave rectifier. So this takes the AC voltage, this line AC voltage, and converts it to DC regulated, DC unregulated. So I'll just draw it out here. You've got your sine wave here, sine wave here, and then you only want the positive voltage to go to the plus supply. So that's one diode, and you can do that, and then it's only half wave rectified. But you can also take the other half of the wave, and then you get, oh, you know what, this should be like that. So when this wave is positive, you get it going to the positive supply. And on the other half of the wave, when this is positive, you get that going to the positive side of the supply. And then likewise, you can have, oh, sorry. I'll just cover that with my finger. You can have this go to the negative part of the supply. So then you'll get a positive hump here and then a negative hump there. So it's not regulated right at this point yet, but then what they add is 2 gigantic capacitors, which are these babies here. These gigantic 1200 microfarad 30 volt capacitors. So those smooth out that sine wave and turn it into like a slightly lumpy sine wave, but slightly less lumpy than it was before. So that's full wave rectification. So you can see that here, full wave rectifier, and then gigantic capacitor over here, and the negative supply over here. And this is actually, you can tell that there's 2 duplicates of the power supply. Positive supply and negative supply, they're actually pretty much the same thing. So you only have to really look at one to understand what's going on. Okay, so that's the full wave rectifier. And then you can sort of see that there is like this section and this section is kind of the same. There's like a diode, capacitor, resistor here, and then this section here. So this is like the positive and negative supply. So let's trace this out. The positive supply.
Say what year this was made.
You know what? I don't know. Let's look for a date code. This says 85-1596, but that doesn't necessarily mean it's 1985. Let me look for another date code.
Okay.
I do not see any super clear date codes. I'd have to actually look at them. I think 80s. I think 80. I mean, it wouldn't be unusual for this 85 to be basically 1985.
Started in 1976.
Yeah, so I mean, it's not the first design they made. This is, you can tell this is kind of more advanced. So, yeah, that's like maybe 85. I mean, it says 85, 1586 on top of here too. Could be 85. I don't know.
Yeah.
Fifth.
It's late 70s.
Yeah. Could be this is one of the later ones they made. There's no date on the schematic either, so it's a mystery. Could be from the future. Okay, so right, where were we? All right, so you have the two sections of the power supply, and it looks like this positive, is even labeled positive, goes over to this group, and then this negative one goes to this group. So this is the positive supply, and this is the negative supply. And then over here, you see there's a transistor, because it's labeled emitter collector base, and it's connected to this chunk of metal. And that lets you know that these are the pass transistors. So this power supply uses these transistors to actually drive the current to the positive and negative. And these basically have to eat the voltage difference between the 15-ish volts, 17-ish volts that you get out of after rectifying line frequency to whatever the output supply is. So if your output supply, let's say you're drawing 100 milliamps from the positive supply at 10 volts, that means that you're drawing 100 milliamps times the 5 volt difference, so half a watt through this transistor. So you can see why they've got these heat sinks. These are just made out of chunks of metal, but you do want to heat sink them because the lower the voltage of the output and the more current you have, the more voltage times current drop, the more wattage you have to dissipate through each of these transistors. Okay, so next up, let's look at the schematic for the positive supply. Do you happen to have this up on the thing? Okay, so let's first look at this section here. So you've got the semi-regulated output from the full wave. So this is going to be, this positive supply at this point right here is going to be about like 17, 18, 19, maybe 20 volts DC. There is this gigantic capacitor that you saw in the back there. That kind of gets it into an okay place, but it's not going to give you a really good, it's not stable. You don't know what, every transformer is a little bit different. Everybody's power is going to be a little bit different. So to make a reference that is known and stable, down here they have a Zener diode. So if you've got, hold on, you've got a somewhere around 20 volts DC, and this is a 15 volt Zener. As long as this resistor is, gives you at least like, I think about 20 milliamps going through here. So this is like, about, looks like they used about 200 ohms. It doesn't matter whether this voltage goes up or down, and it doesn't even matter how precise this is. This voltage is going to be 15 volts within like 3 to 5%, which is not awesome, but this isn't a precision power supply. It's good enough. I mean, if you really want to have an excellent power supply, you'll use, some sort of temperature compensated band gap reference, and then multiply that, from there, or that's what's inside a voltage regulator. But they don't have voltage regulators. Maybe they just didn't exist yet, the kind of adjustable one they wanted. So they just made it with a couple transistors instead. So this is how they got their 15 volt reference from a Zener. And there's one here and there's one here. The one here is, of course, upside down because you want a negative 15 volts. And then over here, we've got the action. This is where the actual voltage regulation occurs. And over here, Q102, you can see this is in the path from the 20 volts to the regulated output. So this is that pass transistor. So yeah, Q102. So that's it. This is where all the power is going to be dissipated from. This is what actually does the heavy duty work. And then Q101, you see it's just connected up with the same collector and the emitter of it connecting to the base. So this is a Darlington configuration. This just basically feeds the current in, gives you a little bit more gain because you need a lot of current in here to be able to pass a lot of, you need a lot of current going to the base if you want to pass a lot of current through the collector to emitter, and maybe you need a little bit of help, so you've got Q101. And this is fed by R103. R103 is it's kind of limiting the amount of current. There's a certain limit of current that's going through here, and this is what is feeding all of the bases. The base of Q101 and Q102. And then over here we've got Q103, which it looks like it's connected to the positive voltage control. This is a potentiometer that's used to adjust the voltage. There's a little diode here as well. And then there's this kind of interesting transistor over here, which is hooked up, looks like sort of backwards, like what's going on here with this one. This is actually interesting. This is this works with R107, and I'll actually diagram what's going on here because it's kind of interesting. So you've got your this is the 56K, and then this is actually this is a Darlington, but we're just going to draw it as a single transistor. And then this goes into a 4.7 ohm resistor. And you're like, what is this 4.7 ohm resistor doing here? Because this is going to the power supply. Why would you want to have something? I mean, it's not a fuse, right? Why would you want to have a resistor in the power path? Well, this Q104, man, it's hard to draw transistors. Okay. So this is 104. So here's what happens. You're drawing current out of this power supply, you're having a good time, and you draw, maybe let's start by drawing 1 milliamp. When you draw 1 milliamp, the voltage across this resistor is going to be 4.7 milliohms. So not that much, whatever, not a big deal. But as you draw more current, let's say now you draw 100 milliamps, now this voltage is going to be for 470 ohms. Sorry. You draw 100 milliamps, this is going to be 470 millivolts. So as this voltage here goes up, this turns on. The more current goes through here, the voltage across this resistor goes up, the base emitter voltage increases, and it turns on this transistor. This transistor turns on, and it starts taking current away from the base of the pass transistor to turn this off. So it does get into a steady state, which you can model, or we could spend a lot of time and have a load adjustable load and see what happens. But basically, this keeps this the current going through here from increasing to more than 0.7, 0.8 volts. More than 0.7, 0.8 volts, this will increase more and more and more. And since this is limited, this 5.56K resistor limits how much base current's available. All of it's going to go through this transistor instead of here. So this is an interesting current limiting method, this resistor and this transistor, limiting the current. Okay, so we got the Darlington, we got this interesting current limiting system going on here. So last up, we're going to look at what Q103 does, and along with this potentiometer. Now we know that this transistor and potentiometer adjust the voltage output because it says positive voltage control, so that's good. So for this, I'm going to draw this larger. Actually, let me. This is what iPads are good for, by the way, for holding your pieces of paper while you draw circuits. So let's see, where were we? Okay, so you've got, this is the 56K, and this is your unregulated positive supply. This is my Darlington, basically. Going into here. I'm going to ignore Q104 because I don't care too much about it. We know what that does. So then there's This is 103. And then this goes to the 15 volts and is adjustable. So this is adjust up and down. And then this goes to the output. So this is the regulated out. And this is just 4.7 ohms. So as this potentiometer gets twisted, somehow the output gets adjusted. And what's interesting is I was thinking about how these things work. It almost makes more sense to think of it as a feedback system, because obviously it's stabilized, so there must be some sort of feedback path going on here. And assuming that you've got a stable feedback, how can you think about what this transistor and potentiometer does? So let's say you have a stable voltage out. Let's say you have a stable voltage out of 10 volts DC. And this is what it's currently set to. You're super happy, and this is about 20 volts DC unregulated. So this is in a steady state. You've got 10 volts DC out. And then this potentiometer goes up. So it gets twisted up. So this voltage goes a little higher. So when this voltage goes higher, then this voltage goes higher, because this is just a following diode, which means that this VBE goes down. Why? Because the output is stable at 10 volts, and so when this voltage goes up, this stabilizes. I'm sorry, this stable output shrinks the difference between this stable voltage and this new change. When the VBE shrinks here, less current goes through here. So this goes down, less current goes through here, which means that more current goes through here, which means that this transistor turns on higher, which means that this voltage goes up. And then it stabilizes when the amount of current going through this VBE equalizes with the Darlington transistor current to keep the voltage output the same. So then if you think about it the other way, let's say you have a stable 10 volts DC, and this potentiometer gets twisted down, then this emitter voltage also goes down, which means that VBE goes up, which means that there is more current going this way, which means there is less current going in here, which means that this voltage then drops. So that's how this feedback system works. I mean, you can model each transistor and think about exactly how much current is going in each one, but if you have a stable negative feedback system, it doesn't actually really matter what the gain of this is or the gain of this is, or exact, what's the drop across this or drop across that, because when you twist this potentiometer, this loop stabilizes so that both of these transistors are happy with the output voltage. It's kind of like interesting. Like usually you think about feedback systems only with op amps, but it is possible to have a feedback system with only 2 transistors. So that's kind of neat. So that 15 volts DC is only basically determining this voltage here. So that's kind of interesting. Okay, so next up, let's look at here. So that's kind of the neat stuff. So then I just wanted to really quickly take a look at the oscillator, because it's very unusual to have signal generators with sine wave out with only like 3 components, because there's like not a lot going on here. What's really neat, and I have never actually seen this in real life, I've only seen this in art of electronics, this little bulb here, so this is a little, it's actually a light bulb, and it's used as a Wayne Bridge oscillator. So like everybody's heard about Wayne Bridge oscillators, but like you never actually see them because they're not really used anymore. Instead, what you usually do is you have a direct digital synthesis of a sine wave, or maybe you get some triangle waves and you chop them up, or square waves and you just filter and filter and filter them until you get a sine wave. But actually, you can get a pretty nice sine wave out of using a Weinberg oscillator. The only thing is that like you really have to make sure this bulb never dies, because that would be sad. But the way this works is basically a light bulb acts as a it has a very sinusoidal. When more current goes through it, the resistance goes down, so it uses that as a feedback path. But I've never actually had to study one because I've never had a light bulb. We never used light bulbs in lab, so that's kind of interesting. And then over here, this is pretty straightforward. There's a class AB. You can see they choose 2 diodes so that you don't have any voltage loss over here. And then that's the sine wave out. And then the square wave goes through this transistor with, looks like it's just a, what's the word? Not chopper. It cuts off the voltage at negative 0.7, and then this one filters that. So that's how you get from 0 to the positive 15. This is the just a follower here. So yeah, this is sine wave, this is AC output, and then this is a DC from 15 to negative 7, and then it's a DC from 0 to 5, and then it just inverts twice. So it's it's pretty simple. And then here you can see the switch. This switch that changes the frequency range, it just switches out which capacitors are connected into this, looks like a little op amp, a little miniature op amp to set the range of frequencies. And the potentiometer is over here. They're kind of neat, very simple, but straightforward. I don't know. Should I look at more scope cam, or what do you think, Mr.
More scope cam.
More scope cam? Okay, well let's
What do you want to do? So is this it? Is this Teardown?
That's pretty much it. I mean, like,
That's good.
this is it. I mean, like, there's a whole lot going on here. I think the most interesting thing is I think they have a cute little power supply. The power supply was really neat because I was looking at it. I was like, hey, what's this transistor? I was like, oh, wait, that's a current limiter. So don't do this normally, but
One more thing on scope cam.
yeah, I'm powering this up. So I thought it would be interesting to, let's get the high voltage stuff out of the way. Actually, you know what? I can, forgot, I can probe this from the top because it's all through hole. Ugh. It's rare that you get to take apart something that's all through hole. So let's check the output of this, the sine wave generator. No, sorry, it's supposed to be turned on. Oh, this is lovely neon bulb. Oh, that's really beautiful. So let's see. Oh, that's the wrong, want the trigger level. So yeah, look at that beautiful sine wave. Great sine wave. So yeah, you can adjust this frequency. And then here, it goes into, let's see, this R16. So R16 is, oh, the resistors are not labeled, but I can just hook onto the base of this. Okay, so you can see this is the first, I'm going to kill this rotary encoder. Oh, come on, there you go. So you can see it's going negative to positive 0.7 volts. And then over here, it gets shifted up because the transistor doesn't conduct negatively, so you get 0 to 0.7 volts, and then on the output, you get, oh, God. Give me 5 volt, there you go. So you get a nice big square wave. And then I just had a curiosity. I'm interested, so you can see, let's look at the, so this is the output from, right before, this is from the transformer. So this is right before any full wave rectification. And then let's look at the full wave rectified. Actually, full wave rectified is pretty clean. But yeah, about 23 volts, that makes sense. You want to give yourself some headroom if you want to get 15 volts regulated out. And then let's look at this 15 volt Zener. Let's see how good this thing is. Oh, it said it was a 15 volt Zener. Let's see. 15. Oh, maybe it's a 5 volt Zener. D106. Oh, you know what? I'm sorry. It's a. You know what? It says point. You know, I can't really read this thing. It looks like it says plus 15. D. Maybe that's the wrong one. You know what? I wonder if D10. No, that's not D106. I want D101. I don't see any. Oh, maybe this is it. Nope. Ah, there it is. That's the negative Zener. Sorry, that's a signal diode, not the Zener. The Zener diodes actually look a lot like 1 and 4000s. Oh, so it's up here, up here. So this is the negative 15 volt, which is actually negative 14.4. You know, Zener diodes. You get what you pay for. And then this is the positive Zener, 16 volts. So it's not like really quite centered perfectly, but it's kind of within reason. You know, if you really wanted a good system, again, you'd have a feedback loop with a more precise voltage reference. But since the person's twisting the power supply knob, you can use the human as your feedback loop. Don't forget to put humans in your feedback loop. And then, let's see, so I see D106. This is the, oh yeah, so you can adjust the voltage this way. I see, so that's the reference voltage. Okay, neat. And then if I plug into the positive, turn that on. So you can see the yellow trace is the reference voltage, and then the output voltage is going to be about 1 volt higher because it has to pass through